In this video, we'll see how elementary row operations affect the span of the rows of a matrix. In other words, how they affect the row space. What we'll discover is that they don't. So let a matrix A have some rows A1, A2, up to AN. Our claim is that performing an elementary row operation will not change the span of the rows. Proof. Well, there are 3 row operations. The first is swapping rows. So, for example, you could take the second row and the nth row and swap them. The span of the original set is the linear combination of these vectors. The span of this set is the linear combination of these vectors. And of course, addition is commutative, so it doesn't matter in the least that you've written these terms in a different order. These are the same linear combinations. Slightly less trivial is multiplying a row by a non-zero constant. So we have these rows. Let's call the row we're going to multiply by something A sub k. And then let's say that we do multiply that row by something. A constant C. And it's our claim that the span of these vectors and the span of these vectors are the same. We're going here to make use of that word arbitrary. We keep talking about arbitrary constants. The span of this first set is these linear combinations. So these C's could be any real number. The linear combinations of this, we've got still these linear combinations. Now, we've changed this vector, so it's an arbitrary constant times this new vector, C A sub k. And it's our claim that these linear combinations are the same. And as I said, the workhorse here is the word arbitrary. C sub k could be any real number. Well, if C is non-zero and C sub k can be any real number, then C sub k times C can also be any real number. So any real number times A sub 1, any real number times A sub 2, any real number times A sub k, up to any real number times A sub n. Down here, any real number times A sub 1, any real number times A sub 2, any real number times A sub k, up to any real number times A sub n. These are the same thing. That's basically the argument we're going to make for the last of these elementary row operations. Multiplying a row by a non-zero number and adding it to another row. It's our claim that this doesn't change the span. So that's somewhere in this list. We'll put a vector A sub I. A sub I is the vector that we're going to multiply by an arbitrary constant and add it to another row, A sub k. And let's ask ourselves, what are the linear combinations of these vectors? What is the span of this set? Well, each of these vectors gets an arbitrary real number in front of it. Like so. And now if we multiply and combine like terms, this will give us a C sub k times C times A sub I. We have a C sub I, A sub I. We can combine those. Now, instead of a C sub I, we have a C sub I plus a C sub k times a C in front of the A sub I. And here, then, are the linear combinations. Compare these to the linear combinations of the original set before we performed this row operation. Those are C1A1 plus C2A2 plus, in front of A sub I, we just have C sub I. And again, these look different until you remember that these C's stand for any real number. And if you have any real number plus any real number times some constant, you can get any real number back again. So if you just select your C sub C sub I, and C sub k appropriately, we can make this be any real number. This is any real number. Really, these linear combinations are the same. So let me briefly summarize this in writing. Theorem, elementary row operations, and thus Gaussian elimination do not change the row space of a matrix. In this video, we argued that Gaussian elimination does not change the row space of a matrix. Now, or rather I should say in the next video, we'll use that fact to find the basis of a row space.